Good afternoon, everybody. It is the final day of August, sort of the end of the summer. Some parts of the country might still have a month or two left to go, but it is back to school time. It is back to work time. And thank you for joining us for our August-September edition of GeoStrata Extra. Today, we have a great presentation on urban waterfront resilience by Steve Dickenson of New Albion Geotechnical. He'll be interviewed by Jeff Dunn, one of our intrepid editors of GeoStrata magazine. We will get to that in just a moment. Of course, I am Brad Keeler, the director of the Geo-Institute. Hopefully you recognize me from Director's Cut, GeoStrata Extra, or one of the 6,800 at this point other things that I am coming to you on your screen seemingly daily. Director's Cut, of course, will begin next week in earnest. We have 4 shows next week. We have Guna Gunalon, we have Jean-Louis Brio, we have GI staff member Christina Scott, and we have Katerina Ziatopoulou from UC Davis. It's a big week. So if you don't know anything about the Geo-Institute, we are a technical society of about 12,000 members housed within the American Society of Civil Engineers. Pretty much all 12,000 are geotechnical engineers or geologists. We would love to have you. You can find out more at geoinstitute.org. We also have a sponsor today. We would like to thank them. The name of the company is MapleSoft. You should check them out. They have a new product they're promoting called MapleFlow. MapleFlow freeform tool from MapleSoft provides a flexible mathematics solution for civil engineering projects. It's a virtual whiteboard style environment that automatically keeps calculations live as users refine, reposition, and develop them. To learn more about MapleFlow, visit maplesoft.com/MapleFlow. So thanks again to MapleFlow for sponsoring today. As I mentioned at the top, we have a great show on urban waterfront resilience. And here to take it away for your viewing enjoyment is Jeff Dunn.
Thank you, Brad. And welcome everyone to the current edition of GeoStrata Extra. Today, I'll be speaking with Dr. Stephen Dickenson, who wrote a As I See It commentary in the current issue of GeoStrata, the August-September issue, entitled Geotechnics and Urban Waterfront Resiliency, Adapting to the Dynamics of Tides, Tremors, and Transportation. 3 challenging T's all in one. The issue theme was marine and coastal geotechnics, and Dr. Dickenson also co-authored an article in the same issue with Samuel Christie, Paul Gunther, and Sharon Walsh, entitled Seismic Performance of a Deep Soil Mixing Grid, a magnitude 7.1 load test at the Port of Alaska. Very interesting article, and I got to act as the lead editor on that one. As Brad mentioned, as the interviewer, my name is Jeff Dunn, and I'll be your host for this GeoStrata Extra session. I'm a senior principal and senior consultant, single practitioner consultant, actually, with our Jeffrey Dunn Geotechnical Consulting, and I'm located in Walnut Creek, California, which is quasi-marine location because we're only a few miles from San Francisco and San Francisco Bay. And I've been an editor with GeoStrata magazine since 2004. Our speaker today, an interviewee, Steve Dickenson, is the president of New Albion Geotechnical Incorporated, a consultancy specializing in geotechnical earthquake engineering applications for major civil works. Dr. Dickenson's consulting, research, and post-earthquake reconnaissance efforts have primarily focused on dynamic soil structure interaction of foundations and the seismic performance of slopes, earth structures, and earth retention systems at ports and coastal facilities. He's led or supported numerous investigations of the seismic performance of various civil infrastructure with an emphasis on the marine environment, involving development on weak soils, deep foundations, and the effectiveness of ground treatment for mitigating hazards, which we're going to be talking about somewhat today. His background, Dr. Dickenson earned his bachelor's degree in geology from the University of California at Berkeley. Go Bears, where I also went to school. But then he decided to head east and work on and obtain a master's degree in civil engineering for Virginia Tech. And then he came back west, back to Berkeley, where he earned his doctorate in civil engineering. At Virginia Tech, it's interesting coincidence that he did his master's working with Professor Wayne Clough, who happens to be the geo-legend in this issue as well. So another connection between Steve and the issue, which is always kind of a fun thing. He's a licensed civil engineer in California, Nevada, Oregon, and Washington, and a board-certified diplomate in port engineering. And he has over 30 years of experience in consulting practice, academics, applied research, and development of continuing education for geoprofessionals. He's mentioned in his bio, he's resided in numerous places along a circuitous path from the San Francisco Bay Area to the Pacific Northwest and to Blacksburg, Virginia, which he didn't mention in writing, but he now makes his home in Reno, Nevada, where he enjoys all the outdoor time he can get. But unfortunately, right now it's so smoky there and the air is so hazardous that I think he's stuck inside by and large 24 hours a day. So that's some background on our interviewee, Steve Dickenson. From just a few introductory comments, when I was working on this issue and preparing for this interview with Steve, it made me think of growing up in Southern California. I grew up in a part of the city of Los Angeles, which is known as San Pedro, even though it's actually part of LA, and it's the port of Los Angeles. And I grew up there watching that port, which at the time was 60 or so years old, but was going through some very large enlargements and evolution as the port changed over from conventional old style cargo to containers, which is just revolutionized shipping all over the world. And growing up, I'd visit numerous ships. I could look out of our backyard at the port and watch from the distance things going on. In elementary school, we went on field trips to the port all the time. I remember one really exciting one was to the Chiquita banana boat docks, where they unloaded bananas from Central America. We visited tuna canneries because we had a tuna fleet there. We also sometimes on foggy nights were treated to fogs that smelled like fish and not in a good way. And I remember another thing from when growing up there is that there was almost every day you'd hear the sound of distant pile driving hammers working. And they were working on nearly constant port construction and redevelopment projects, as well as installing the first container cranes that were built at the port, of which I don't know how many there are now, numerous ones. I ended up having an awful lot of friends that ended up working in marine trades, everything from shipbuilding to being officers on ships, both in the US Navy and in the Merchant Marine. And I look back on my career, I worked on a number of ports projects, particularly early in it, and most of those tended to be related to conversions of wharf facilities to containers from what used to be called break bulk cargo to containerization. But for some reason, my own career path, I didn't specialize in ports work all that much. I enjoyed the projects I worked on, and they still interest me a good deal, but I went into some other things, even though I still dearly love the marine environment and ocean, and particularly beaches. So having a chance to interview Steve about this one is particularly enjoyable and interesting from the perspective of having grown up around this sort of thing and not knowing what it was necessarily technically, but still having a big interest. So with those introductory comments, one last thing. During the interview, if you have any questions for Steve, please type them into the chat box, and for the video feed, which is down, should be down at the bottom of your screen. And as time allows, we'll do our best to address them either directly or kind of roll them into some other questions we might be discussing. So with that, Steve, welcome to GeoStrata Extra. I talked a little bit about my background in how I didn't go in towards Marines, but what led you to your career focused on coastal marine geotechnics, and what education training helped you along your path?
Yeah, happy to share that, Jeff. And thank you for the introduction. You've teed it up very well for me with our primary theme here, that everything's always changing at ports and urban waterfronts. So thank you for the background there. And thanks also to Brad for the very energetic kickoff for today's GeoStrata Extra. So thank you so much. Pleased to have the opportunity. And I am also delighted that to be in the same issue of GeoStrata with geo legend, Professor Wayne Clough, who was a wonderful mentor for me at Virginia Tech. So delighted to get started there. So with your question, what drew me to coastal and maritime and ports? Well, it starts, for most experiences during childhood, my parents provided lots of opportunities for us to explore tide pools. We were into clam digging, abalone diving, fishing, scuba. So I've always had an affinity and fondness for coastal areas. As far as education, as an undergrad, I really enjoyed geomorphology and the dynamics of estuaries, bays, rivers. As a graduate student, Professor Mike Duncan at Virginia Tech threw us some very thought-provoking and challenging homeworks. One of them was an underwater slope failure, an excavation in San Francisco Bay mud at the Port of San Francisco. And the other one was an interesting dynamics issue of a rail-mounted gantry crane running into a fender system that was pile supported. So very much soil structure interaction. But the fact that Professor Duncan could bring that experience into the classroom was fantastic. And that was at the Port of Virginia Norfolk project. As training, as I transitioned into my first real consulting job at Dames & Moore in San Francisco, I had a wonderful mentor, internationally known expert in soft ground engineering, Demetrius Koutsaftas, who really helped guide me on all things San Francisco Bay mud and the challenges associated with it. So that was the training part of it. And then finally, it all culminated in 1989 with the Loma Prieta earthquake. And that hit while I was back at Cal as a PhD student. And that changed the course of my research in about 15 seconds. And spent a lot of time after that doing post-earthquake recon with my classmates at Port of San Francisco, Port of Oakland, Port of Richmond, and many coastal areas. So that's the long background there. That's what got me into it.
Definitely some big events that led you on your career path, without a doubt. So in your commentary, you focused, and a lot of our questions are going to be related to the Port of San Francisco, and particularly a resiliency project that's ongoing right now, I think. And you have I think a slideshow you wanted to show first to give some historical context. So let me bring those up. Bear with me a second here. Click on the right box and go back one slide. Okay, there we go. Have at it.
Oh, fantastic. Thank you very much, Jeff. Yes, for the benefit of my colleagues, both in the Geotechnical Institute, but also in COPRI, that I'm also a member of. Just a little background, a quick history to demonstrate again the main point that the waterfront is always changing. So I'm going to focus on the Port of San Francisco. We're going to start in 1853, 5 years after gold's discovered. The gold rush is on, and you can see the lower portion of San Francisco at the time. It's tidal flats and the soils associated with that, which were largely fine-grained marine sediments, San Francisco Bay mud. Next slide, please. Less than 10 years later, you can see the development in San Francisco. You can still see areas that haven't been completely developed along the shoreline, and you start to see some small piers and development occurring. So we're starting that evolution of the waterfront. Next. And in around 1890 or so, we now have intermodal transportation networks well in place, with the maritime cargo coming in on your right, surface transportation, including the rail lines coming in. So the transportation system is really evolving quickly. Next. Now, that was shaken up a bit in 1906 with magnitude 7.9 earthquake, the Great San Francisco Earthquake, and then the fire that followed. Here we have a shot along the waterfront with some lateral spreading, liquefied ground, and then movement of soils on that soft bay mud. So we did see ground failures during 1906, of course, in the waterfront areas. Next. And then this is just the iconic San Francisco ferry building, which was damaged, but made it through the 1906 earthquake. And you can see a bit of the transportation network there with trolley cars. But obviously the ferry building still very much part of the San Francisco waterfront. Next. San Francisco did rebuild, as we all know, and just to show a couple of slides for folks interested in the development and construction and the methods and means. Continued development of the San Francisco waterfront, which was not all in place at the time of the 1906 earthquake. So much of this postdates the earthquake, but continuing evolution, development, and redevelopment of the waterfront. Next. 1917, continued development. We see pile driving, concrete piles going in. And so we're really developing the waterfront. And the other thing that we can't see here is that dredge depths for ships are starting to get deeper and deeper. So we're now excavating into and through the soft San Francisco Bay mud, which was providing challenges. Next. And again, back to transportation. I like this slide because it demonstrates a variety of modes of transportation, going from the right-hand side of the photo with signs for the ferry system. Passenger ferries were still very much in use. This is roughly 1930. We have, again, the railroad still working along the Embarcadero. We have the streetcars, we have automobiles. So a very diverse array of transportation along the waterfront, all changing and adapting with needs over the decades. Next. And then just an aerial shot showing the old finger piers next to the ferry building, the kind of triangular looking piers. Those have all been replaced. So things are constantly in a state of flux along the waterfront. Next. And then we jump ahead a few decades. We have the elevated highway structure, the Embarcadero Viaduct, designed and constructed in the late 1950s, early 1960s. We now have very congested waterfront. You don't see any rail lines anymore, and the passenger ferry service had really tapered off, but we see this large structure. This photo was taken about 2 years after the 1989 Loma Prieta earthquake, and astute viewers can see damage to that pier. There you go. Thank you very much, Jeff. Damage. That structure was later demolished and removed, opening up the waterfront and restoring things like the streetcars on rails. And so again, adaptability and change to the transportation needs. Next. And speaking of evolving, some things, it's back to the future, so to speak. It's what goes around comes around. We now have in the San Francisco Bay Area, the Bay Ferry system, which is part of a resiliency program to provide post-event, post-disaster waterborne transportation. It's the WITA system. You can see the WITA ferry terminal recently constructed. And so we now have a wonderful network of ferries that commuters can take. And so we're kind of back to ferries and some rail lines along the waterfront. Next. And then one thing for geotechnical engineers to keep in mind, and we'll talk a little bit more about that as we continue, is this gradual change and transition from a working waterfront, meaning more commercial cargo handling, to recreational, publicly accessible areas along the waterfront. This being the Pier 15, Pier 17 area at the port, which is now a wonderful hands-on science museum, the Exploratorium. and publicly accessible. And that brings on challenges for geotechnical engineers that we'll get into. So, and I believe that's it, Jeff.
One more, I think.
Oh, one more. Okay. Well, the postscript, I guess, that again, things are dynamic and always changing. Here we have a barge-mounted drill rig working away on a project which is now a floating fire station at Pier 22.5 along the Embarcadero waterfront. So things are always in flux, and we now have this new very important aspect of response and recovery along the waterfront, San Francisco, the floating fire station. So I owe a debt of gratitude to the Port of San Francisco and colleagues who've provided a lot of these slides for me. So thank you very much, Jeff.
Okay, great. Let's go back. Okay, stop our screen sharing. And that provides, I think, a real good historic introduction to the port and some of the things we'll talk about in our question and answer today. One of the things in your commentary, you mentioned that port and marine facilities can have challenging soil conditions. And in my career working in the San Francisco area, certainly working with San Francisco Bay mud, I always found that to be interesting and challenging, kind of fun, but sometimes for clients, not so much fun in terms of impacts on project costs and so on. But it led me to think about it. I mean, you know, most ports, they're built on rivers or bays, and sometimes, you know, like the Port of Los Angeles, they built a big breakwater to kind of pacify the Pacific Ocean and make it suitable for a port. And as such, therefore, they're kind of the end receptor areas for sediment flow, and there can be, like in San Francisco, in a lot of ports, a lot of historic filling that's gone on overground, like marshes and wetlands and that sort of thing. So in your experience, are bad soil conditions more the rule than the exception, or, you know, what might you have to say about that?
I would say yes. The prevalence of weak soils, compressible soils, is the rule more often than not. So it's the depositional environment. It's geology 101, low energy, geologically speaking, the depositional environment. So whether it's a bay, an estuary, or along our inland waterways, flooding and overbank deposits, infill into old oxbows, lots of fine-grained soils, and that's what we're usually up against as geotechnical engineers. Makes it challenging and fun for some of us. So you also mentioned fill, because that becomes a significant issue for redevelopment projects when we consider the behavior and performance statically and seismically of the fills that are placed, because a lot of these fills are over 100 years old, depending on where we are and the age of development, and very vulnerable to deformations under applications of static and seismic load. So whether it's a riverfront or a bayfront, we have the need for filling to raise grades for piers, wharves, quay walls, for offloading of ships. So yeah, between the depositional environment and the fill that we place, often very challenging.
Yeah, okay. You mentioned in your slideshow as well, and this is something I'm quite aware of working in the San Francisco area, but San Francisco, you know, at one time was a vibrant port and evolved over a number of years, starting particularly with the gold rush in the 1850s. And now it's not a working port so much as a recreational and you know, community interest area. You mentioned the Exploratorium Museum, and there's other, you know, museums and facilities, lots of restaurants along there. Have you found that in your experience working in working ports, like say, for example, the Port of Oakland by comparison, or the Port of Los Angeles, or other ports in like Alaska, where you worked on your article, that it's a different kind of animal or a very different focus in the projects in terms of, you know, more different land uses?
Oh, very, very much so, Jeff. And the Port of San Francisco is I can assure you, not lost any of its vibrancy. It may be a transition from, as you say, a working port, a cargo handling port, to a bit more recreation, but very, very dynamic. It is different, though, than, say, a cargo container port, as you mentioned, Port of Oakland, Seattle, Long Beach, LA. So what I'd like to share for my colleagues in the GI is that this transition brings with it a number of challenges and things that they should be aware of. When we transition from a commercial port, which does not generally have public access, to something involving tourism and recreation, we've now opened up the area through redevelopment to the public, which is fantastic. The public wants to be along the waterfront, wonderful views, very dynamic, but the codes and standards that we use as practitioners change in that redevelopment. We go from, say, the ASCE COPRI 6114, for those members from COPRI who are with us, to ASCE 716, for example. And particularly with respect to seismic, the standards are different and the requirements for us as geotechnical engineers change. So this accessibility for the public changes the rules of engagement, and I think appropriately so. We have things such as ADA requirements that we need to evaluate, higher seismic load levels for design, sea level rise over different design life can be a consideration. So, and then I guess the last thing I would share is that for many of these redevelopment projects, and some in the east part of the San Francisco Bay Area I've been involved in, we're transitioning from World War II era piers and wharves that were Navy, US Navy, to redevelopment involving light commercial and residential. Well, if anybody's going to be buying a nice new condo or townhome right on the, they want to be as close to the water as possible. So it provides interesting challenges for us as we evaluate how that ground might move, say, during an earthquake. So different standards and codes, different focus, and geotechnical engineers need to be aware of that.
Have you had any projects where that change was anticipated up front, maybe, or, you know, have you ever run into that? What I've seen is like ports kind of seem to develop, like, you know, tenants, marine tenants might decide to go elsewhere or need different facilities, and then some other use comes in. But have you ever seen any that are really anticipated?
That's a good question, Jeff. And my interpretation of that is I have seen and been involved in projects where ports for new construction have anticipated that work could be staged or phased over a decade, and that there might be changes in the type of shipping, containerized cargo, dredge depths required, things like that. So they can anticipate that, but they remain commercial in nature. Most of the existing older port facilities that I've been a part of and in redevelopment, it's not been apparent that the agency, the port, considered that at some point in the future, and this could be decades in the future, that this might transition from a working port, cargo handling port, to more of a publicly accessible or recreational area. So I've not had experience where the planners and the design teams decades back had anticipated that their working pier could end up being, say, an exploratorium, for example. But I do have worked on a number of projects where this redevelopment is ongoing right now. Port of Seattle with Pier 62, waterfront areas in San Diego, Alameda near Oakland, and the East Bay that I know you're very well aware of, where Navy facilities, many of these are decommissioned military facilities, Navy and Air Force, that then are converted to residential areas or, again, light commercial.
Yeah, you mentioned Alameda, and I did some work on that. I know, and lateral spreading is a big issue there, mitigating that. So in your discussion, in your commentary about the Port of San Francisco waterfront Resilience Program, to use the formal name. You mentioned a first principle that unmitigatable movements must be considered in seismic design, especially like in San Francisco for deep deposits of Young Bay mud. For those that don't know, it's a very weak marine clay. What kind of magnitude of movements are you talking about there?
Okay. To start, that principle, that guiding principle, actually is well stated in the preface of the code, the ASCE code 36114 for piers and wharves, and it states that quite clearly, that depending on the soil types, deep deformable deposits of marine clays or very thick layers of liquefiable sand, it may not be economically viable to completely mitigate to the point where we have no movement of the waterfront. So for those involved in seismic design, we need to take more of a displacement-based perspective. We need to allow for some tolerable level of permanent deformation and accommodate it. So your question with respect to what levels of deformation are we looking at, it would depend on the seismic hazard level and the performance requirements. And for ports and harbors, for example, we have our operating level earthquake, which we would anticipate and we would want that the port would be in operation very shortly after that level of shaking. And the deformations associated that could be anywhere from 0 inches to a foot. So we'd want to be somewhere in that range, and that would generally be acceptable. These are just general guidelines. And then for our contingency level earthquake, a higher level of seismic demand, we would expect some downtime, some loss of serviceability after the earthquake. Those deformations could be on the order of 1 foot to 1.5 feet. So these are the targets that are commonly used. So it's important to convey to designers and the owners, the agencies, that some level of deformation should be anticipated.
I'm curious. I've noted in working with, particularly with high rises in San Francisco, but how a lot of the general public aren't really up to speed on the fact that, you know, a code-based design doesn't mean that there's going to be damage. I mean, there's hopefully not loss of life or serious injury, but buildings could need a lot of work. And it sounds, you know, very similar thing, not surprisingly, in marine facilities with different thresholds. Do you find that a lot of the stakeholders or can deal with this concept of, you know, some movements, the need for repair, and how do you best communicate it to them?
Well, with respect to stakeholders, for the sake of this discussion, I would view the stakeholders as the owners, managers, the agencies, and these would be non-technical specialists who are part of the owner planning team. And so the stakeholders will grasp these concepts, the idea that there will be some, I like to use the term tolerable displacement as opposed to tolerable damage, because we are all averse to the idea that after all the money that we put into a repair or a mitigation, there could still be some damage. So it's good to craft it from the perspective of there's tolerable displacement or deformations that may require repair after the design level event. So the stakeholders I've found will grasp the concept, provided that examples of disruption are provided for them. And this would hold true for any sort of natural hazard, be it a flood, a tsunami, a hurricane, you know, as we've had with Hurricane Ida, again, now in the news. Providing stakeholders with photos, with examples of what has been seen in the past, they come to realize that some level of deformation is acceptable, provided we can design for that. Now, the other thing is introducing concepts of displacement-based design. And without getting into the weeds, you know, for the sake of the stakeholders, sharing with them what this really means, getting away from merely just a factor of safety to an estimated range of displacements and likely performance, be it geotechnical or structural performance. So we are now engineers as educators, and I like to think of it that way because one of the services we provide to our clients is education, and this is one that I've seen time and again.
Okay, yeah, sounds good. Thank you for those comments. In talking about the seawall project, the resiliency project in San Francisco, and talking about mitigation strategies to improve that system along the waterfront, you spoke of in your commentary it struck me as a menu for evaluating a menu of proven soil improvement methods and or structural elements to improve the stability of the seawall and the waterfront. And that often the solution along various lengths of what's a fairly lengthy seawall involve more than one method, two methods that seem to work very well together. Can you give us an example of that?
Certainly, and the menu, or buffet, if you will, on the soil improvement side, we have stone columns, vibro methods, DSM, jet grouting. On the structural side, we'll have piles, drilled shafts, relieving platforms have been used, and a variety of other techniques, anchor systems. So that is the menu. And I think what ports around the world are finding, particularly with respect to seismic concerns, is that the optimal solution requires integration of, say, soil improvement with a structural approach instead of a reliance on just one method. And examples that I would encourage our viewers today to pursue and look into with really nice websites and very engaging interactive types of examples. Port of San Francisco has a wonderful website for their seawall resiliency program. And in Auckland, New Zealand, there is the K Street or the Key Street seismic strengthening project where they've used jet grout and piling. So you asked about combinations. A combination that I've seen routinely is use of either a jet grout or a DSM with deep foundation elements such as piles or drilled shafts. So there's a combination of structural and geotechnical approaches that have been implemented at ports. I guess one final one for now, the Elliott Bay Seawall project in Seattle, which was a major project and highlighted in many ASCE publications. Use of DSM, jet grout, relieving platforms, a variety of things. So I think it's the main point here, and the takeaway would be for geotechnical engineers to be thinking in terms of an integrated solution instead of a reliance necessarily on just one approach.
Okay, thanks. You also noted in your commentary that it's important to balance mitigation strategies from what you've selected off this menu, as it were, buffet, as you mentioned, and that being important so that improving one aspect, you don't make another aspect of the project's performance worse now or for future projects that might be, like you said, sometimes projects are phased or something like that. Does this happen very often? I mean, it's not unusual in projects of all kinds that you have to balance things, but that where, wow, we have a great solution to improve the seismic performance, but it really messes up something else. So is it difficult to thread that needle? Or?
Sometimes, yes, and there can be unintended consequences. And I think an analogy that I think many of our viewers today and our colleagues here would understand by analogy, we think of excavations, say deep excavations, where we've all run into situations where we may be running into previous development. It could be tiebacks from adjacent properties. It could be piling from previous projects. It could be a whole variety of things where, again, it's unintended, but there could be consequences. So with respect to seismic and sea level rise, which was the focus of the commentary, one of the big questions is, would the mitigation that we may use for seismic performance interfere in any way with subsequent applications for sea level rise? Because we're focusing on two different aspects of dynamics along the waterfront. And so we need to do what we can as geotechnical engineers to anticipate that in working with the client, if it's understood that things might be phased over a decade or longer, that what we do now, say for the sake of seismic mitigation, which could be a DSM buttress, for example, how might that aid in or interfere with eventual sea level rise adaptation that we might want to implement? So there would be an example.
Okay. So you have to deal with, as you mentioned in answering some of these questions, multiple hazards. And I wonder, particularly going forward, like here in California, and I think along a lot of the west coast of the US and other parts of the world, seismic inputs are well understood. I mean, some of us have gone through pretty significant earthquakes in our lifetimes. But then you throw in sea level rise, and in some areas, particularly as we're seeing this week with Hurricane Ida, storm surges, which can be enormous. It obviously gets quite complicated. And some of these threats, like sea level rise in particular, don't necessarily follow a path where, earthquakes, we can kind of learn from them as they occur and look back at performance and so on. But we don't have that kind of record necessarily to predict the future for sea level rise. Do you find that that's at all complicating?
Complicating, yes, very much so. And I think for projects that are multi-hazard in nature, it could be seismic and flooding, it could be hurricanes and storm surge and other related issues with respect to levee stability, but a number of geotechnical applications that involve evaluating multi-hazards. We could address these in a probabilistic framework, and I won't spend a lot of time going into the probability and how we would combine these natural hazards. But I guess what I see in practice most commonly is that the hazards are treated independently. They're uncoupled, even though we may realize and acknowledge that sea level rise will likely have an impact on, say, waterfront stability, and particularly seismic stability. So these, while they are interactive, they are connected, they're often treated for practical purposes separately. And then we evaluate how to add those two things together. So it can get complicated. So part of that's beneficial for stakeholders because they grasp the idea of these hazards in isolation first, and then we can talk about the combination. I guess one thing I'd like to also add, and this has been a very important aspect of many port redevelopment projects, and I thank my colleagues for lengthy discussions and very thoughtful discussions on introducing the fourth dimension, which is time, which on many of our projects serving clients as consultants, we don't think as much about the long-term impacts, the adaptability of what we're doing. And that is becoming more and more important along the waterfront. So that aspect of the time dependency on when these hazards may occur. And very simplistically, we could think of the likelihood of earthquake ground motions happening anytime, depending on Poisson distributions or other distributions that we may use. But very simplistically, those earthquake motions we should be prepared for at any given time. Whereas with sea level rise and the associated flooding that would occur along with that, we treat that more as a gradually increasing risk with time. We have projections. As you point out, it's difficult to forecast these things, but we do have projections, estimations of what sea level rise will be over the time horizon of interest, which is generally 100 years or so. So that can be melded into that multi-hazard framework.
Okay. Well, you already answered my next question about how to adapt mitigate, so that's pretty good. I know a few projects I've worked on, not marine facilities recently, but near San Francisco Bay. In one of the design criteria is an assumed elevation to be above anticipated sea level rise. And I know some of the cities and counties and other government agencies are establishing what they say is okay in our jurisdiction. This is what we anticipate, and you need to design for it. So it is being applied a lot of different places. We had actually, Steve, this will catch you a little by surprise, but we had a couple of questions here that have come in from the audience related to mitigation and some of those impacts. One of them was, are there any new techniques to lower the deterioration of waterfront structures due to erosion that you're aware of? We've been talking about seismic and that sort of thing. Certainly some of these soil improvement techniques might be helpful, but anything comes to mind there?
Certainly, and if I'm interpreting the erosion as, say, scour due to tidal currents, wave action, prop wash is a big issue at ports, and river currents. Various methods of ground treatment could be used to solidify areas that may be prone to scour. We have the whether I want to call it tried or true, but the rock fill riprap approaches that we're all very well aware of, which is not new technology at all. Maybe the application might change a little bit, but in combination with other approaches. And so I would be thinking in terms of a solidification type ground treatment approach could be worthwhile. But even that would need to be protected in some way. We wouldn't want to have ground treatment elements necessarily exposed to a high current, an abrasive scour type of situation without some kind of rock armor.
Okay, good. Well, another question that came up, kind of this would relate somewhat to, you mentioned, progressive dredging at a lot of ports, both to deal with sedimentation and as ships have gotten larger and larger. Yes. In this questioner asked, many urban areas have disturbance limits on river or bay sediments due to the presence of pollutants from a history of manufacturing. And, some of the marine activities, ships weren't always so good about not just dumping stuff into the water, I know from experience. How have you coped with that during projects? I know San Francisco has issues with that, certainly, probably just about every port does. Is that another limiting factor, I guess? That's
always a primary concern, the environmental aspect of dredging. I've been involved with projects that involved everything from old finger piers, for example, that ships no longer use finger piers in different areas. I'm thinking of areas, say, along the Willamette River near Portland, Oregon, where some of these piers, there have been proposed sediment basins, confined dredge disposal areas. So there's not only the act of dredging the materials, but then the transport and the eventual placement. And that is always an issue at ports. Any type of waterfront development, that would be key. So certainly anything turbidity, curtains, Steel sheet pile walls have been used for containing contaminants. One project in the Bay Area that I was involved in, where we had contaminants through fill and sand layers within the bay mud, using slurry methods. So a slurry wall type of approach, and DSM as well. So there are a variety of ways to try and contain those contaminants during redevelopment of an old port or an old military facility.
Okay. So switching gears just a little bit, in the article that you co-authored on the Port of Alaska Petroleum and Cement Terminal, PCT, I noted that the facility was being designed to be serviceable because it was felt to be very, very necessary, of course, right after the design earthquake, which was a magnitude 9.3 subduction zone event, which whenever I see magnitude 9, it's like, whoa. How much deformation was designed for at this facility so that, it's stay in service?
Yeah, good question. Good question. So the magnitude 9-ish earthquake would be very similar to what was experienced in Anchorage in 1964, the Good Friday earthquake. So there is experience there in the waterfront. And these were very stringent post-event operations requirements. And in portions of this terminal were designed to be accessible and in operation within a week of that magnitude 9 earthquake. So not necessarily the entire facility with all backland areas, but the waterfront areas to be in service and to be able to transport petroleum products, primary fuel distribution area for Anchorage within a week of the earthquake. So the deformations were again a function of the seismic hazard level. Again, we mentioned the operational level earthquake earlier. That, as I recall, was a 3-inch deformation limit. The contingency level earthquake was a 6-inch target tolerable deformation, and then the MCE, which was used as a collapse prevention life safety, was on the order of 18 inches. So those were the ground deformations, but what we all need to be aware of is that while geotechnical engineers, we can have these target limits, which is very helpful for designing the layout of ground treatment. But the other thing to keep in mind is that these are usually pile-supported structures, or will have sheet pile structures, and they will deform with the soils. And so we also have the soil structure interaction going on. So in addition to the limits that we might have on a ground deformation, we're also looking at strain limits within piles, for example. So very much a soil structure interaction application. But those were the rough limits for the Anchorage project.
Okay. I noted in that article too, it was not surprising, but it emphasized that the analyses and the design that were done for that project were supported by a robust field investigation and lab testing program with some pretty, state-of-the-art testing methods. For a large project, at least large linearly, like the San Francisco seawall mitigation project, do you have, the support of a robust program like that, the budget to support it? Or I know there's probably lots of old historic borings of varying degree of accuracy and usefulness, or is that part of that project, or where does that stand?
It's definitely a part of the San Francisco project, and I give the Port of San Francisco tremendous credit for not only compiling in a nice digital repository all of the geotechnical information that they've been able to pull together going back 100 years, a fantastic archive, but they also understood the need for a targeted and integrated geotechnical evaluation, which involved a wonderful program of in situ sampling, testing, site characterization across the 3 miles of waterfront that we were looking at. The design team did a phenomenal job with that. And then also all of the laboratory testing, including static and cyclic testing of the San Francisco Bay mud. So a tremendous program. And I will point out that there was a theme session on this project where the port and their project design team, their assessment team, had a theme session at the Ports 19 conference, which was held in Pittsburgh. And that theme session was not only just standing room only, there were people in the hallway looking in through the doors. It was a fantastic session. The proceedings of Ports 19 provide a really nice overview of that geotechnical investigation that was led by Fugro, with SGH providing structural engineering. So to answer your question, Jeff, it was very much a part of this project and continues to be a valuable part of the project. Okay,
well, that's certainly good to know for sure. We had another audience question that relates to terrible soil conditions. This person asked, does any specific waterfront area or structure that you've worked on come to mind as having terrible soil conditions, aside from Bay mud?
Oh, terrible. A good use of terms there. So terrible might denote different things to different people. But when I think of terrible, I think in terms of how challenging was that situation. Now, terrible could be the weakest soils we've ever seen, which have been aware of sites along the Gulf of Mexico and developed there with some very, very soft, very compressible soils. But there have been situations around the world on projects that I might consider to be a bit more terrible, so to speak, in the sense that the constraints provided by the existing infrastructure made it challenging to tackle those geotechnical issues that we were charged with mitigating. So terrible in my mind could include a web of buried utilities, lifelines. It could be power, it could be water, wastewater, and we have that going on many waterfront areas. And then to throw that in with site development at the surface and poor soils, that is very, very challenging, and that we run into quite a bit. So to take poor soils, weak soils in a well-developed area, and in an area that's been developed over 100 years or more. The Boston Big Dig comes to mind. The Port of San Francisco project, Port of Seattle. Those provided very, very challenging conditions for geotechnical engineers. So that whether we want to call it terrible, certainly it was more than just the soils that made it problematic. It was the existence of existing infrastructure that made us really work together as teams to come up with in many cases, innovative solutions.
Interesting way of looking at it. Not the soil, but other challenges. Well, we're just about used up our hour here in a good discussion. Last question I have for you is kind of looking forward, and you talked about looking forward, looking at sea level rise and that sort of thing, and the fourth dimension of time that you mentioned. But what challenges in coastal and marine geotechnics do you see that need to be tackled in the future that aren't part of the practice today? Sea level rise goes without saying, I guess, almost, yep. But anything else?
Well, there are a couple of things I'd like to leave our viewers with today. And I'm going to stay away, I guess, from the analytics. We've within the practice, we're always talking about the best new models and the the constitutive models and how they're implemented in nonlinear dynamic displacement type of analyses. And Mike Beatty and Scott Anderson did a wonderful job on a GeoStrata extra. So I thank them. So they've covered that one. So I'll leave that one aside. But there is, as I see it, in many of the folks involved in this today are aware that there is an evolving emphasis on community resilience. And this is resilience through a whole variety of things. Changing nature of development, commercial development, evolution of waterfront areas, and changes maybe from a working port to more recreational or residential. But also with respect to natural hazards, the resilience to earthquakes, hurricanes, flooding, sea level rise. And so this idea, and we'll use the term holistic because it does pop up quite a bit, this emphasis on looking more long term as to how does our project, maybe it's only one portion of a long waterfront, but how does that project contribute to an overall community waterfront resilience? And that's something that I believe provides challenges because it's multidisciplinary and requires that we work with larger teams. And so I see that as not a challenge to avoid, but something to embrace, but to keep in mind that this is where many municipalities are focused. And I know New York City and Lower Manhattan, very, very proactive, particularly after Hurricane Sandy and the flooding that they experienced, that this resiliency after natural hazards. So a more holistic approach, that's one thing. The other thing, as we've already mentioned, is again, this dimension of time. And for those of us in practice to consider in working with clients that they may be viewing many of these very extensive, very expensive waterfront mitigation strategies may evolve over decades. And we need to be mindful of the fact that, again, the solutions that we come up with now should be adaptable for future work. We don't want to, through the unintended consequences, be providing an impediment to future mitigation. So that could be a challenge as well.
Okay. Well, going to be challenging going forward, not surprisingly. So we did have one other question, which is kind of off topic. Somebody asked about the Millennium Tower and the ongoing settlement. And I know that's not marine, so I won't ask you to answer that one. But it's interesting as that building is located in an area that was filled in from San Francisco Bay. And it was just, I'll take a slight stab at it, is like there's plenty of very well qualified people looking at the increase in settlements during the mitigation construction, and the building had not stopped settling. The settlement was slowing, but it had not stopped. And of course, anytime you have construction and you're disturbing soil, there's the chance for movement. So that's a pretty medium answer, but I don't know if you want to add anything, Steve, to that or not, but or
well,
just leave. You go ahead.
Yeah, you've teed it up well for me. I guess the short answer from where I sit is that we need to be aware of, where is the zone of interest here? Where is the zone of high foundation loading? And much has been made over the past few years regarding the fact that there was fill placement here. There was some bay mud, but that is, as I see it, was really not the cause, or didn't, by cause I would mean substantially contribute, it seems, from what I've read on the settlement. The settlements are, appear to be associated with the older bay clay. So it is marine in a sense, that it's the older bay clay that underlies the San Francisco Bay mud. So it's the transfer of building stresses into that lower layer and how it's performing. And as you've pointed out, that anytime we would be implementing construction involving excavations or ground treatment, we are disturbing a portion of the soil before that strengthening takes place. So that apparently could be contributing as well. But anything I would be throwing out right now would be conjecture. And as you pointed out, there are lots of very well qualified folks in the geotechnical community working on that project.
Yeah. I know I worked on the buildings right next door and across the street, but I'm not party to the data from anymore. So I hazard at saying much more. So with that, Steve, I want to thank you very much for a great discussion. And to all of you who attended our session today of GeoStrata, it's going to be available shortly on the Geo-Institute YouTube section of that platform. And if there's anything you'd like to hear again, or if you have colleagues who missed the live session today, it'll be available usually just within a few days after today. So with that, thank you again, Steve. And Brad, I'll turn it back over to you.
And thanks, Steve, for a great presentation. It really feel like, I guess we can't say interdisciplinary because it's all civil engineering, but you really did a great job reaching out to our environmental and our coastal brethren today. That was really entertaining. Thank you. And that's not a word I usually use for these things. Informative, maybe, educational, maybe, but it was a really entertaining presentation. I really enjoyed that today. And thanks again, Jeff, for doing such a great job on the interview. And thanks to all our viewers for your great questions today. That's a huge part of the value of these things, are the questions that we get from the live viewers. So we really appreciate it. Thanks for sticking around till the end. If you like what you saw, and I think you did because you're still here, click subscribe, click get notifications. We will let you know every time we post something to the YouTube channel, which is, as I like to say, very frequently. If you have not made your contribution yet to the 25th anniversary Student Participation Fund drive, you can do so still. Go to geoinstitute.org. You can get started there. Get a handsome thank you gift like one of these 25th anniversary pins, $25 and up. $250 gets you a beautiful GI dry fit shirt. $2,500 gets you in the President's Circle, which is a very special thing, and we give you all kinds of recognition for that. So if you are so inclined, make your way over there, where you can also find out how to join GI technical committees, find your local chapter, find out about GI awards, and all kinds of other stuff. So thanks again, Steve and Jeff, for doing this today. I think this was a very worthy GeoStrata Extra, and we will see everybody again for the next episode in October.